Hello and welcome to this presentation. My name is Nicolas Oberli, and today I'm going to show you some anti-debugging tips and tricks for embedded devices and especially Cortex M microcontrollers. This idea is not new. For a long time now, computer sharewares or games implemented several anti-debugging tricks within the codes to prevent software piracy or game cheating. Maybe some of you remember the isDebugger present Windows API or the melt ice tricks created to avoid the debugger to be attached to the process. Nowadays, we can do exactly the same on microcontrollers, and this is what I will show you today. On embedded devices, having access to the debug interface usually means game over. You have read and write access to the firmware, read and write access to the registers, and you can even look at the code while it's running to better understand what it does. For a reason that I cannot really explain, a lot of devices that you can buy on the market today have this debug interface wide open. Some microcontrollers have ways to disable this debug interface, but again, it's quite never done. So my idea is how, as a firmware developer, you can add software countermeasures to a debug access that is not authorized. Before we start digging into the countermeasures, we first need to understand how the debug interface on those chips works. So first of all, we have SWD, which is the alternative of ARM for the JTAG interface. SWD uses two wires, the clock and I/O. This I/O is bidirectional, so usually the debugger sends a command and the device replies directly on the same data line. It is always the debugger that drives the clock. This SWD interface is a bridge between the physical world of the debugger and the internal debug bus within the core of the chip. The internal bus used for debugging purposes is called the DAP for Debug Access Port. Having access to this DAP from an external debugger is made through what is called the DP for Debug Port. Then, on that DAP bus, there can be one or more APs for access ports. Those ports are connected on a bus, and each of those APs have a specific ID and different registers that you can read or write from or to. This is pretty similar to the JTAG DAPs. Here comes a bit more complex part. You cannot directly access an AP register from your debugger. You always need to query the DP first and ask it to query the AP register for you. So every time you need to make a query to a specific AP registers, you first need to select the AP with the AP cell register, then use the AP bank cell register within the DP to select which registers for the AP you want to select. And then you can read or write the registers called RDBUF, which contains the value that the DP queried on the AP for you. Since that protocol was a bit hard to understand, I recreated it from scratch using Python, and I used HydraBus as the target interface. This way, I was able to first create low-level functions like writing on the bus, reading on the bus, bit per bit, read status bytes, know when to read data or write data. And then I created higher-level functions like writing to the DP registers, and then select APs, then read from APs, write to APs. And I also created wrapper functions to, for instance, scan the DAP bus to map all the APs available, because sometimes there can be, as I said, multiple APs on the same DAP bus. For this example, we will scan the whole DAP bus to look for specific APs. But first, we need to instantiate the PyHydraBus SWD module and call the businit function, which will reset the SWD interface. This is done by sending 50 clock cycles, a specific value, and then 50 other clock cycles to reset the interface. Once the interface is reset, it is possible to query the DP register at address 0, which contains the ID code. The DP is always enabled whenever the debug interface is available on the chip, but the internal DAP bus is not. To enable it, we first need to set the bits debug power-up requests and debug reset requests for the control stat register within the DP to enable it. Then, it is possible to query the register at address 0xFC for all APs from 0 to 255, and if the result is different than 0, that means there is an AP available. Here we can see that there is only one AP available, and within the next slides we will see which one it is. Now that we know how to access the APs, we need to understand how we can access the core system memory. This is done by using what is called the AHB AP or the MEM AP, depending on the documentation. This AP is created by ARM and is able to query any part of the core system memory and send the data back on the DAP bus. So the main concept is you first set the TAR register with the address at which you want to read or write. And then you can read or write the DRW registers to either read data from that specific memory address or write data to that specific address. There are other features in this MEM AP, but that depends on the Cortex M series that you are using. So now that we have access to the whole memory regions, you will tell me, how can we read or write specific CPU registers? Well, in ARM, those registers are set at specific memory locations that are written in the slides here. And using the MEM AP, you can either read the register value or change the register value by writing to this specific address. All the registers are available directly from here, and everything is well documented directly from the ARM website. Those addresses are also common to all Cortex M families, be it M0, 1, 3, or whatever. But this would be way too simple if you could access the MEM AP directly and it could read or write the memory while the core is running. To avoid this kind of problems, you first have to tell the core that it's currently being debugged by setting a specific field in a register called the debug halting control and status register. This register is always set up the first when you are starting a debugging session. Otherwise, the AP will always reply with an error when you are trying to read or write data. So, since this register is the first one to be set when you are starting a debugging session, from within the firmware, you can also read that register and say if the debugger is active or not. Unfortunately, you cannot disable the debug access from the firmware. This is only available from the MEM AP and nowhere else. Also, this doesn't work on Cortex M0 chips, since this register is located somewhere else and the core doesn't have access to it. Here on the left, you can see the source code, and on the right, you can see the running device. This line will select the register and the specific debug enable bit. Those variables come from the ST SDK, but you can find exactly the same on other manufacturers' SDK, or you can also hardcode the values. Now, within the infinite loop, I will call this function to get the status register, and if the debugger is detected, I will turn this GPIO off to turn on the LED, otherwise the LED will stay off. Now I can show you the OpenOCD configuration. It's a classical one, and you will see that when I run OpenOCD, the LED will turn on. There we go. That means OpenOCD started the enable and the LED turned on. That means the detection works. There is a catch with those detection techniques. If the debugger is stepping through the code, it can see the detection and change its value accordingly. Fortunately for us, OpenOCD first starts by enabling the debug on DHCSR, and then in a second time, it will ask the CPU to halt. So we still have some time to make sure that the detection will be detected and handled. But there is a way to manually set both debug en and ask the CPU for halt in the same write, thus bypassing this kind of detection. For the next technique, we'll try to detect if a debugger has set hardware breakpoints within our code. But first, we need to understand how the core handles those hardware breakpoints. In the documentation, there is a mention of the BPU, or breakpoint unit, available on Cortex M0s and M1s. There is a different unit for Cortex M3s and more, but we'll get to that later. This BPU works with a different set of comparators. If you set a specific value in that comparator, and if the program counter is equal to that value, the core will automatically be halted and a debug event will be fired for the debugger to handle it. This BPU has to be enabled globally before being used, so you can check the specific enable bit for the BPU to make sure that there is no breakpoint available. In this example, we will use the FPB to detect the debugger. So here I hard-coded the register value because it's not available directly from the STF SDK. And I will query this specific bit, which is the FPB enable bit. Otherwise, the code is exactly the same. If we detect a breakpoint, we will turn on the LED. Otherwise, we will turn it off. Back to OpenOCD. For the moment, nothing is happening because we didn't set any breakpoints. And if we run GDB, set a breakpoint, then run the code, the LED turns on. The next technique uses a special instruction, which is breakpoint. That instruction is used to create software breakpoints. Whenever the core executes this function, it will fire a debug event, and usually the debugger has to take care of it and break at this specific point. But the thing is, if the device runs the breakpoint instruction and there is no debugger, that event will escalate to what is called a hard fault, which is basically a hardware fault, and it's kind of bad. But the good thing is we can use this specific hardware fault, detect if that was a breakpoint instruction, and then resume execution if there was no breakpoint. Otherwise, the code will change. So when you enter the hard fault, you can query the specific registers and see if the hard fault was caused because of a breakpoint instructions. So on Cortex M0s, you can check the DFSR registers, or on Cortex M3 and more, the HFSR registers. There's a bit dedicated to the breakpoint instruction. That means that in your hard fault handler, you can query this register, see if that was because of a breakpoint instruction, and if that is the case, that means that there's no debugger attached. Otherwise, you need to take action. Now we have two problems with this technique. The first one is all the saved registers when entering the fault handler are relative to the breakpoint instruction. So if we want to exit the handler, we need to update the saved PC to point to the next instruction. The second problem is that when we are entering a fault like this, the execution state is not anymore in thread mode or in normal mode, it's in interrupt mode. So we need to get back to the code in the correct execution state. If you are looking at the ARM documentation, it will tell you that you need to jump to address FFFFFF9 to resume execution in the previous state. Now that we know everything, we can create our own fault handler that will detect if this was a debugger event or if this was another kind of hard fault. In this example, I created a debugger detected global variable that is turned to 1 if a debugger is detected and 0 otherwise. I will use the hard fault handler to reset that value to 0 whenever no debugger is present. First of all, I will check the HFSR register and look for the debug event bit. And if this one is present, that means that the hard fault handler has been called because there was no debugger present. That means I can safely set debugger detected to 0. You can look on the right that the LED is still blinking. That means that the core is running freely. It's not stuck because of the hard fault handler, just to prove that this example works. Then we need to change the PC value. So these are the 3 lines that will get the saved PC from the stack, add 2 to it because of thumb mode, then store it back on the stack. I will then restore the value of R0, and then I will branch to LR, which is when entering the hard fault already set to the magic value FFFFFF9. In any other case, the device will just be stuck. You usually add an infinite loop there just for debugging purposes. I will start the code by setting the LED off, set debugger detected to 1 by default, and then query the debugger status using breakpoint, and I set an arbitrary value of 8. Then if there was a debugger here, I will turn the LED to solid on. Otherwise, I will let it blink and loop infinitely. The good thing with that technique is that usually the hard fault handler are not really looked upon by reverse engineers, which in that specific case is a mistake. And you can see that if I run OpenOCD, the LED stays solid green. That means that our detection worked. We can also see that within GDB, the code is stuck at the breakpoint instruction. That means that now that there's a debugger attached, all those debugging events will be trapped by the debugger itself and will make the reverse more complicated. We have now seen different detection techniques. Now it's time to look at how to implement them within your firmware. The first technique is to use a timer. Using a timer, you can run a specific function every millisecond or even less. And within that function, you can, for instance, detect the debugger and set a global variable. This technique is quite useful because it doesn't need to be integrated everywhere in your code. You can just set up the timer, set up the appropriate function, and then just need to have a look at this specific global variable. If you are using a real-time operating system, you can use a dedicated thread that will continuously monitor the debugging status. If the debugger is detected, the thread can also directly act upon this. For instance, during InsomniHack on a CTF challenge, we use this exact method to clear the RAM whenever somebody tries to debug the chip. You can also use the detection value to be included within the computation of any other part of your code. For instance, you can create 2 different paths, one when the code is debugged and one when the code isn't. That way, starting the reverse engineering process, you will have a lot of different paths to analyze, but only one will be the correct one. Again, this is just to annoy reverse engineers, and with enough time, a correct skilled attacker will still be able to access the correct parts of the code. Now that we have seen several detection techniques, we are able to go a bit further by modifying the code at runtime so that even if attackers have access to the debug interface and were able to dump the firmware, they will have a hard time figuring out exactly what it does. For that, we can use the FPU, the Flash Patch and Breakpoint Unit, which is the evolution of the FPB and is only available on Cortex M3, 4, and more. This has exactly the same functionalities as the FPB, but as an added bonus, you can remap specific instructions at several positions to others directly from RAM. The FPB is used to remap the code from one location to another. This is quite useful, for instance, if you have the code in read-only memory and you want to set up a patch, or while debugging, you can set up a semi-permanent patch while debugging to a specific function. But you can also use the FPB remap as an obfuscation. For instance, within the code, you have a call to a specific function, but with the FPB, in fact, you are calling another function. And we will see later that the debugger cannot really understand what is happening, and it will still think that you are using the correct function and not the remapped function. In this example, I created two dummy functions called return1 and return0. Return1 is used within the infinite loop to be set as the GPIO value. So in that case, return1 should set the LED off. But it is on. So we will see how I set up the FPB to make return1 point to return0. First of all, I created an array and set the FP remap register to that specific array within the RAM. Its first cell contains a pointer to return 0. This will be our destination. Then, in the FPB comparator, I set a pointer to return 1. That means that whenever the program counter steps into return 1, it will instead be remapped to return 0. Here I'm enabling the FPB. And again, this is the destination. Now, within the infinite loop, whenever I call return 1, instead it will call return 0, then set the GPIO to 0, thus turning the LED on. If I run OpenOCD, what it does is basically remove all FPB entries and automatically set the LED off. We can also see in the code, if we step by step trace the code, that every time we try to call return 1, it will, exactly as it should, return 1. But at the execution time, it will do exactly the opposite. If you read the ADI documentation, you might stumble upon the semi-hosting features. Semi-hosting is a way for the debug application or device to query or to put data on the debugger computer. This is quite useful. For instance, the device can write log files directly on the debugger computer. It can also read test data from the debugger computer to the device, or it can also simply be used as a printf equivalent, but directly from the SWT. So how does it work? Once the device is connected to the debugger, it can execute the service request instruction, and this instruction will generate a debug event that will be trapped by the debugger. The debugger will see the trap ID, which is 0xAB, and it will know that it has to query the R0 register to know the operation, and R1, which will be a pointer to the structure for the syscall. It will then fetch all the data needed for the syscall, execute it on the local machine, and if it needs to send back results, it will, and then it will resume the execution on the target. This feature is supported by OpenOCD, but is not enabled by default. To enable it, you first need to connect to the target. Then you can write the command arm semi-hosting enable to enable support for semi-hosting traps. You have an example code on the right, which is a basic printf that will print data on the semi-hosting interface. For this example, I created this print semi-hosting function that uses as the first argument the file pointer on the host, which is stdout here with 1, a pointer to the data to be printed, and the size of that buffer. Then to execute it, I will set the syscall number 5, which is syswrite in R0, a pointer to the data in R1, and call the breakpoint with the value AB that will be trapped by the debugger. Then the infinite loop will just print hello GreHack, which is 16 characters, and with a delay. Now we can run OpenOCD. You won't see anything yet because it's not enabled by default. So we first need to enable the semi-hosting within the telnet interface of OpenOCD. Then we'll reset the chip, and you will see in the upper corner that the string is printed every time. If you look at the ADI documentation, you can find the whole list of syscalls that are available. One of them is called sys_system. And yes, it does exactly what you think it does. It takes an argument from the device, and the host will execute this command using the system call on the hosts. On the right, you can see that OpenOCD already supports this, and there is no mitigation and no checks about what is being executed. For this example, I'm creating exactly the same function as before, except that now I'm using a different syscall. My command will be killall OpenOCD. The syscall I'm using, syssystem, has the system call number 18. We will set that to R0, and all the rest is exactly the same as before. This function will be called within the infinite loop, so it will run whenever OpenOCD is connected. We can now run OpenOCD, enable the semi-hosting interface, but now nothing. We can try to type Ctrl+C, whatever, OpenOCD just crashed. In the previous example, I didn't want to mess up with my machine, so I just killed OpenOCD. But you can think of way more creative ways to annoy people trying to access your device. For instance, a fork bomb, or removing the home directory, or also download some scripts from the internet and execute it directly on the machine. That was the last trick I had for you today. Now it's time to get to the conclusions. First of all, I'd like to say that the whole ARM debug interface is way more complex than I thought when I started this project. There are a lot of other functionalities, and if you take time to read the documentation, you will find other ways to improve your debugging skills or find new tricks like those ones. Also, the things that I presented are actionable, and you can already use them within your firmwares to implement debug detection. But let's be honest here, those will only be used during CTF challenges in the future times. Also, if you are creating a new device, please make sure that you disable the debug interface if you don't want people to mess with your devices. Nearly all the chips have a way to disable this interface, so please use that. That's all I had for today. Hope you enjoyed and learned a thing or two. I'd like to thank the GreHack organizers for all the work they have done. And if you have any questions, feel free to ask. I should be around to answer them. Bye.
Okay, thanks for your presentation. So are there some questions? I think one from Doc. He said, why the debugger doesn't override the breakpoint handler, or am I missing something?
Well, when you set up a breakpoint instruction or you use a hardware breakpoint, it will call the debug event handler first. And if you don't have a debugger attached, that event cannot be used. So the core will, let's say, raise the exception to the hard fault, which is the ultimate fault that you can have. So this is the way we do it, by forcing the core to execute the debug event. And since there's no debugger, it will raise to the hard fault. And this is how you can detect that there is a debugger or not.
Okay. One question is, do you have an anti-debug trick for CTF?
Maybe, let's say I won't spoil future challenges.
Yeah, that's that was the remark. Like we would know what to do, what to try for the next CTFs.
Yes.
So one other question is how to atomically attach and stop the CPU at the same time.
As I said in the slides, the only way is when you connect first to the SWD-DP. When you set the debug enable register, you can set the alt request bit at the same time. And on some cores, not all of them, at least I didn't try all of them, but some of them worked, some other not. But on the ones that work, you can enable the debug and stop the core at the same time, which is quite useful in that specific case.
Okay. So thanks for the answer. Another question is, so is there or will there be an article or blog post as a reference?
There are some blog posts on my company website on SWD as a whole. For all those anti-debugging tricks, I might do something, but at least I will upload them to GitHub. So you have access to the source code so you can analyze them, see how they work. And I will also upload the slides. And yeah, I hope to write a blog post, but we'll see.
Okay, thanks. And also, okay, one more question is, are there such tricks in other CPUs besides ARM?
There might be on x86, but I didn't really look into those ones.
Okay. So you have a lot of things on the IRC. So yeah, really thank you for your presentation.